Hello everyone, it's August the 9th. Alright. Oh, we've done this. Maximum strength in a group. We've done this. So we can move on. Search in a rotated sorted array. This is there's an integer array num sorted in non-decreasing order, not necessarily with distinct. Before being passed to a function, num is rotated at an unknown pivot, such that the resulting array is. Isn't this the same as the one we solved the other time? It's similar to searching rotated sort. I think this is the one, right? We did it just maybe a few days ago. Right? Yeah, 2 days ago. We did this 2 days ago. Given the array after rotation, return true if target is in nums, or false if it is not in nums. Num is guaranteed to be rotated at some pivot point. I think the answer is no. I think we can still binary search this. So basically we just say we have 2, 5, 6. Right, 2, 5, 6, 0, 0, 1, 2. 0, 0, 1, 2. Right, 2, 5, 6. So if we do binary search, right, we'll hit somewhere, and again, it'll be the same thing. We compare to one side, right? We'll compare to one side, and if it's larger than the left, I mean, let's regroup the idea. We have a target, right? So if the target, if the mid is larger than this point, right, then it must be on this half. Then we can do this, or we can do this. But I think there is some change because we have duplicates now. But duplicates usually shouldn't matter. So basically, if we don't land on the duplicates, it's the same, right? If we're larger on this side, then we know the mid will be on this half. Then we say if it's on this side, if it's larger than, right? If it's larger than this, or if it's within this one, we're gonna do this. Within the other one, I don't know. Do you think there's any change in this? I don't think so. Because if you have, like, say this, right? If you're landing here, and if this is the middle, if a target is larger than this, and then you will still, I don't really think there's any difference in this. I don't think so. I think we can use the same idea. And if it's within this, otherwise we do that. Yeah, we should say smaller or equal to. If it's larger than the front, right? Or if it's smaller than the rear. It's larger than the front. And if it's inside this, otherwise we're gonna do this. I don't think so. I think it should still be the same. not 100% sure, but let's take a look. Okay. Int low equal to 0, high equal to nums dot length minus 1. While low is smaller equal to high, mid is low plus high divided by 2, right, and divided by 2. And then we say if nums mid is equal to target, turn true. Right, otherwise we say if nums mid is larger equal to nums low, okay, then we say if target is smaller than if we do larger equal to, okay, so if it's smaller than because the high never really go down, the low will go up. Maybe we should do larger equal to, yeah. So if the target is smaller than nums mid and target is larger equal to nums low, if that's the case, then then high equal to mid. High equal to mid, I think should be smaller equal to, right? Oh, I don't have to handle mid because equal to I already handled. So that. Else, if it's larger than or it's smaller than, right? If that's the case, then low equal to mid plus 1. We need to push it to the right hand side. Right? If nums mid, else num is smaller, right? Then the low. If you're smaller than the low, then you're gonna be on the other side. Then we say if you're on the other side, then it has to be if target is smaller than nums high, right? Target is smaller, or we can say smaller equal to nums high. And mid is larger equal to mid is smaller than, so mid is this, right? So if target is smaller equal to nums high and target is larger than nums mid, in that case we'll say low equal to mid plus 1. Else high equal to mid. Actually I can say minus 1, right? High equal to this minus 1. And then if we do this, then we return false. Okay, let's try this. I don't think the inclusion of repeated will have any effect. Let's give it a shot. Oh, I think it does affect. It's wrong. Ugh. I thought it won't. All right, that's okay. Let's nums targets. That's okay. 1 0 1 1 1. Target is 0. Answer is true. Search. Wow. Oh my goodness. A lot. Initially. All right. Targets. That should be boolean. Yep. Okay, so what was this? 1 0 1 1 1. I forgot. 1 0 1 1 1. 1 0. Oh yeah. 1 1 1. I have this because these two can be equal. So if they're equal, I think that's a little bit tricky, right? Because you put this in, it can be equal to the front or it can be equal to the end. Ooh, I see. So this doesn't really work because it's larger than. Huh. But I think that's the only edge case is if these are all the same. Right? That's the only edge case. Yeah, because on this side it goes up, on this side it goes this. So these two can be the same. If these two are not the same, yeah, if they're not the same, then it's the same, right? If that's not the same, then it's the same. If this and this is not the same, then we can always separate. This one will always work. But if these two are the same, then what do we do? If these two are the same, then when you get in, you basically say, I don't know, man. I don't know which side I belong to. So I probably need another one when this is equal to, right? If your mid, right? If your mid is equal to. So if the mid is larger than this, or the mid is smaller than this, right? Otherwise, the mid is in between these two. The mid, but this is larger than this, right? But the mid is in between these. The mid is smaller than this. No, the mid is if the larger is smaller equal to. So we say num's mid is gonna be smaller equal to num's low and larger equal to num's high, right? But then we also know num's low is larger equal to num's high, which means yeah, so this value is in between these two. Is it possible? I was trying to say it's smaller than low, smaller equal to low, so it should be on this side, but it's larger equal to high, so it should be on this side. So which means when this happens, that means these two are the same, because this one I says high is, I mean this is smaller or equal to this thing, right? Because I rotated, right? But this is always smaller or equal to this thing. So there shouldn't be anything in between these two, right? There shouldn't be anything in between these two. And the only way for this means this is equal to this. Yes. So when it's equal to, what do you do? Well, when it's equal to, just like this case, what mid is here, I mean, equal to this, equal to this. Well, if it's equal to, and we have at a certain point, right, at a certain point, it's equal to, maybe what we need to do is look around. Do we look around? I mean, yeah, because I can have a bunch of equal, something is small, the bunch of equal, right? So when you land on the middle, you really don't know. You really don't know. So what I can do, one way to do it is just eliminate all the duplicates, right? We can eliminate all the duplicates, but then the runtime will be on plus log n, right? On plus log n. Can definitely do that, which will make it work. But I'm trying to see if it's possible without doing this operation. Yeah? Trying to see if it's possible without doing this operation. So when that happens, we need to see in the mid, I don't know where it is. Right? I don't know where it is. So if I really can for the middle, this is the same. So one possibility, right? Because this side has to go up. So it could be this side is going up, but this side stays still, like this, right? And this side needs to go up as well. And yeah, or we can say this side stays still, and this side goes up, right? And this is not this. This doesn't really matter because I can be this, go up, this, it could be any, right? It could be any, like that. And then we just handled in the middle part. I don't know. What do you think? I intend to just remove, go in, and remove the duplicate. Then can you do it without remove the duplicate? Can you? Can we find the pivot point? I mean, if you find a pivot point, yeah, what's the difference? Right, you find a pivot point, then everything will be solved. Easy. Alright, you find a pivot point, you just do binary search on both sides. That's it. The thing is, I don't want to, right? I don't want to find a pivot point. Because if you want to do that, you might just as well just search through. So the idea definitely has to be. Now, I don't think it affects, but I just I don't know. Yeah, your low and high is the same value. The mid, they're all the same. So there definitely is one side is going to be all ones. And the other side might have, then you don't know which side to go. And maybe we can check. You cannot really check. You cannot really check. Check for what? Alright, check for what? I don't know. What is? Hold on. Let me solve this one first. Java array contains. Array.contains, right? Wait, hold on, actually I'm not sure. Arrays as list.contains. Array utility dot contains. Array utility dot contains. Array util dot contains. Is that arrays? Utils. Array util s. I'll probably have it imported. Probably have to import it. Oh, wait, hold on. It doesn't exist. Oh, Apache Common Lang. It doesn't exist. Alright, I just use this one. Then as list. We can do that, right? Nums. Can we do that? No, we cannot. Because it has to be a reference type. It cannot be a primitive type. Dang it. This one will work. But that's not a purpose. This is ON, right? But we need to find out. We need to find out. I don't know. Is login a possibility? I feel it is a possibility. I don't know. Binary search. Jesus. ON was okay. O login. You do walk. What's the solution again? Yeah. Yes, yes. This is the one. So you're saying we just start moving. Oh God. When this happens, we just start moving. I mean, if target is equal to the start or equal to anyone, then that's done, right? So this one thing what I'm trying to say is once you become equal, you just start moving both towards the middle to remove all the duplicates. So after you do that, once will get to the end, and the other one will go to something that's not the same. And by doing that, you're eliminating the duplicates. I think that's what it means. Start to mid end. Both array mid and the target are lying F. Both are doing the same sort. We have no option but to move to next search space iteratively. Oh, in worst case. So basically what it's saying is this is all fine, right? This is all fine. What it's saying is if this is larger than elif and nums mid is smaller than nums low, right? If it's smaller than nums low, then yeah, so have another else. So this is the case. Nums mid equal to nums low equal to nums high. So when this happens, we just do low plus equal 1, high minus equal 1. There's no way to, yeah, there's no way to get out of this. No way to get out of the situation when nums mid is equal to nums low equal to nums high, because we do not know which side, which half, right, to search in the next round. Thus simply move low and high inwards, yeah, by one step, by one index. So on worst case, O log n best case. I hope that shall work. No. That is interesting, to say the least. Oh, this is large, this is high. No? Huh? That is interesting. 13. Ooh, understanding is not right. I say I'm in and they're the same, so I just shrink. Both come in, both come in, both come in, both come in. How come this one doesn't work? Larger than low, no. Smaller than high, no. So they're equal. And, oh, they are equal. But then it's also not equal to target. So I remove both sides. I remove both sides, remove both sides. And at the end, this one I can see 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Can do 3 more. 1, 2, 3. So this is the last one. Right? Is the last bit. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Actually here. It's larger than no. It's smaller than. Oh. If it's larger than. If it's smaller than. Can do it that way, huh? Or we shall just check. Like if it's equal, then we do this. If it's not equal, then we do the other way. So if it's larger than, otherwise we say it's on this side. Yeah, you know what? Let's do it more explicitly. We say if nums mid is equal to nums low and nums mid is equal to nums high, right? When that happens, low plus equal 1, high minus equal 1. So this is to remove, skip, right? Skip all the duplicates. Then we can say else if, then this will be else because we already skipped everything. The idea is the same. The idea is the same, but we make it more explicit. Oh my god, what the hell? It's not right. We say mid equal, then we will do. Then in this case, 0, 1, that will be 0. Mid is 0. 0 is equal to, and this is not true. Huh. And then mid is larger than low. No. Oh, I think maybe larger equal to low. Because initially it is larger equal. No. Yeah, it's large or equal to low. Large or equal to low. But why the mid is here, right? It's not large or equal to low. Then we go here. Then target is smaller or equal to high. And high equals mid minus 1. Why is this one not right? Yeah, it should be larger equal to, right? Well, it took a lot of efforts. I guess it's every single time you do this, it takes a lot of efforts. Remove duplicate. Okay, basically just remove all the duplicates. But you have to be very explicit, right, when you remove. And then it's always removed from both sides. And then, yeah, this should be larger or equal to low. Because if it's equal to low, you're going to stay on the left-hand side. You cannot go to the right-hand side. It does make sense. Yeah, it doesn't make sense. Okay. This one's done. Oh, we can go back to Python now. Greatest common divisor traversal. What the hell? Zero index integer array, and you are allowed to traverse between its indices. You can traverse between index I and j, I not equal to j, if and only if GCD is larger than 1, which means they have common divisor. For every pair of I and j in nums, there exists a sequence of traversal that can take us from I to j. If it is possible, traverse all such pairs. 10 to the 5th. Jesus. Alright, so we have 2, 3, 6. Every single pair, right? So 2, 3, 6. We have 0, 0, 1, 2, right? So we have 0, 1, 0, 2, and then 1, 2. 0, 1, 0, 2, 1, 2. That's the 3 pairs. Alright, 3 pairs. So basically 3 choose 2. So 0, 1, we know 0 to 2 is good, so this is good, right? What the hell? 0 to 2 is good, and then 1 to 2 is good. So to do 0 to 1, I can do 0 to 2 and then 2 to 1. So we have these things, right? So I need to know if every pair is possible. Every single pair is possible. If you have from one, if from one you can go to every single one, yeah, then it's always possible, right? If you start from one index, you can go to every other index. Then for all the other index, you always use this one index as a bridge to go to everybody else. So yeah, so if you find a universal one, then yes. So what do you say? If you have a node, right, you have a bunch of other nodes that can go. If I have one node that can go to bunch of node, and you have another node that can go to a bunch of node, right? And then as long as these two nodes they can also go to each other, then it's a connected graph, right? It's a connected graph. So what we can do is we go through everything, we find the connected graph, we find which things are grouped together. We can union find to do this, right? We can union find, which means we can say indices, these are together. How do we know that? Yeah, basically at the end of the day, you just want to see if they all are together, right? They all belong to the same group. Okay, so union find. Yeah, so we're gonna do union find. So for each index, you go to all the other indices and try to see if they, but that's slow, right? That's slow because you have to find every single pair. You don't know the pair. Right? And of course, if you find something that works, then yeah, it will be nice. It will be very nice. So basically, you want to see how can we do this? You start from one value, and you try to see if another value exists. Or you 10 to the 5th. I was trying to think. 10 to the 5th. Well, 10 to the 5th, that's 100. Right? So maybe we can. Yes, maybe we can factor every single one. You know, just factor. Every single one we factor. Because 10 to the 5th, right? Nums I, the maximum is 10 to the 5th. So if we do square root 10 to the 5th, it's 316, right? So we can find all the way to 315, all the, all the prime factors, right? We find the prime factors. Yeah, we find the prime factors. So how do you factor primes? Yeah, you start with 2, you get rid of all the 2's, and then you start with 3, right? And then you try to find 5, and then no, it's 7, blah blah blah, all the way, and all the way to what? All the way to its square root, right? You go all the way to its square root. And so here's what I think. All right, here's what I think. I will write a function. I'll write a function to the prime factors. Okay, so for each value we have all its prime factors. Then we will list out prime factors, let's say it's 2. We have blah, 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 blah. So they all belong together. Prime factors 3. They all belong together, right? So prime factors. Yeah, so we can say def factor. So given an n, well, factor will give me a list of these prime factors. Okay, so n. We'll do 2 first, right? Rest equal to this. While n equal to 0, n divided equal to 2. Okay. Can we? If not rest dot append 2. Okay, so 2 is done. And now we're gonna say f equal to 3. While n f is equal to 0. If not rest or rest minus 1 is not equal to f, rest dot append f, n while n, my bad. If n mod 2 is equal to 0, okay, else break. This is also true. While n, if n mod f is equal to 0, n divided equal to f, else, so we get rid of it, n plus equal to 2. Alright, until we get to what? Get to, so we so we'll divide, so the f will get bigger and bigger and bigger, right? The f will get bigger until we f get to a point. So limit, right? Lim shall equal to math times qrt n, or do an int, right? While n or f is smaller than lim, smaller equal to the limit. Then we keep going, That's not n, that's f plus equal to. Then we will return the rest. Okay. Then we say we need a union find. What's the union find? DSU. Parent. Right, self dot rank. Right, that's fine. px py, find x, find y. If px is not equal to py, if self.rank larger than self.parent py equal to px, elif rank px smaller than rank py, then self.parent px py, else parent px, no, rank, no, py equal to px, self.rank px plus equal 1, turn true, turn false. Okay, that's union find. This is the factor. It's right? The maximum you can get is the SQRT of this thing, right? SQRT of this thing. Yeah, because it cannot be bigger than that. So if f is within range, you should keep trying until f is out of range. So now I can say DSU equals DSU land nums. That's a total number, right? Then what we gotta do is go through every n. We do the factor. So for n in nums, f's equal to self.factor n. Okay, so we factor out n given all these, and then we need to see who is in it the last time. So we need to say factor dict. Okay, then we say that's actually going to be in enumerate. Then we can say for f in this, if f not in factor dict, then factor dict f equal to I, which means this factor I is belonging to this factor, right? Then we don't do anything. Else, if this factor is already in, then we can say DSU.union factor dict f and I. We'll union these two. And then the new one comes in, I'll union these two as well. Right? So we go through all that. Basically, we go through all of them. And for I in range land nums, I need to say DSU.find I, just to, finally shrink all the things. Then we need to see the number of, if it's possible, it's all. So we need to go to the parents. They should all have the same parents. Return len set DSU.parent is equal to 1. Two, 3, 6. That shall be true. 3, 9, 5 shall be false. Oh shit. I think it's 1, n equal to 1. Ugh. So n larger than 1. Is this one right? I have one more test case we didn't go through. 4, 3, 12, 8. Is it right? Huh. Slow. Very slow. TLE. How many did we pass? Oh, 916. We're almost there. I don't know, man. Do we not to do this? And that could be a slow part. Oh my god. Oh my god. Oh. Maybe I can set it. Remove all the... Wait. What you're saying is, yeah, I can set this, right? I can simply don't go through all of them. We go through unique nums equal to list set nums. Unique nums. This is the same thing. It's the same thing. Oh, shoot. Hold on. So I need to do this is also unique nums. Unique nums. Does this one work? It works. I'm not sure if I need to do this though. There's always a contention. I don't know. I mean, do I need to go through? Yeah, I think we should. Of course, it's gonna be unique nums. All right, let's try this. Get the unique nums. Huh. Oh. Ha. Ha. Edge case. This is an edge case. Oh gosh. Wait, hold on. We start with 1. Wait, hold on. If it's equal to 1, is it good or is it bad? Output should be true. No, output is true. Expected is false. Oh. Oh. Wait, hold a second. These are extreme case. So 2, 2. Yeah. Holy crap. Yep. 2, 2 is true. 1, 1 is false. Gosh. Now what? Well, what we can do is check the uniques, right? If we got more than one value, then it's fine. It's totally fine. Oh, hold a second. I think if you have a 1, you're always doomed, right? Because Yeah, if you have a 1, you're always doomed. Huh. Then I don't even need this. You kind of do need that. Can I enumerate a set? Dude, that's bonkers. Can I enumerate a set? Oh, you can. You can enumerate a set. And honestly, I don't really care about the index. I'm already changing. So I can do this. And oh, God. Right? Then I can say if 1 is in unique nums, then return false. Because if you have 1, then the GCD is going to be 1. So that's a false. Then DSU is this. Then I can do this. I can do everything. Right? I can do everything. Alright, come on. Come on, show me. Show me. Let's do this. Come on, let's go. Let's go. Yeah. Are you kidding me? Oh. Wait, hold a second. Is it all false? I hate edge cases. If you have 1, then you don't move anywhere, so it should all be false. No, if it's 1, it should all be true. To traverse between all such pairs. Well, I don't even have a pair. It has to say I is not equal to J. And for every pair, nah. To traverse, I hate this one. So okay, so we add another edge case. If it's equal to 1, then we'll return true. It was just adding edge case 1 by 1. Nah, I don't know. I mean, you said traverse, right? And it says it has to be at least 2 indices. Now you're telling me you gave me only 1 index. It's undefined, right? It's undefined. I can say it's true, right? Because you're already there. I can say it's false because you cannot read traverse. That doesn't matter. All right, 4th time. Come on. We dealt with the duplicates. We dealt with this stupid 1 issue. We dealt with the... Oh. Okay, so that is the final nail on the coffin about this method. So this method doesn't work. It does not work. How many did we get? 917. This one's 916. Okay, so we just get 1 more. Oh, I see what you're doing there. Bunch of... Yo, don't tell me they're all... Are they all prime numbers? Ah, you prick. They probably the majority of them probably are prime numbers. And if the majority of them are prime numbers, then yeah, I see how it's not gonna work. Because if the majority of them are prime numbers, then at least this part would take a long time. No, not this part. This part, the factor part, would take a long time. Yep. And unique will not do any good. I mean, I can, get the largest num and sieve it to get the number of prime values, and then it will make the factor easier, so I can skip a lot of the values. Yeah, I can do that. I mean, might as well just go, let's say, prime numbers. I know, that's my last ditch. Prime numbers smaller than, let's do 1000. Right? Oh god. Yeah, it's not all that much. Oh, you gotta be kidding me. Give me a list. There we go. Alright, so we have these. Yeah, so self.primes. These and these need a little bit more. I think 317 doesn't work because 317 squared is larger than, larger than 10 to the 5th. It's larger than 10 to the 5th. Okay, so we go to 313. Perfect. Alright, this is the prime. So now the factor becomes super easy. Alright? Then we just say, while this a for p in self.primes, while n larger than 1 and while n larger than 1 and n p equal to 0 and divided by the p, right? But how do I know that it's getting smaller? Good question. And I don't want to do this check every single time. Has p false. Okay, has p equal to true. And at the end, if has p, rest.append p. Okay, and if n is equal to 1, n is smaller or equal to 1, then we break and return rest. Okay. Oh, this one doesn't work. What happened? Self is not defined. Really? Huh. We have to initiate, huh? Okay, this is a last ditch effort. Cheating. Sort of. This won't work. Well, it does. You know what? I can even do better. Screw you. Prime factors, right? So we can just say, if n is in self.primes, return n that itself is, right? Otherwise we do this. probably even faster. I don't know. Go for it. What? No way. No way. One zero 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 seven. 20014. Expected true. I give it false? That is bonkers. Wait, hold on. I changed it. Hold on. I changed it. Hold on. What the hell? Oh, shoot. If it's nothing, return res. If if res, else then n itself is a prime. Oh, what? How did I not get 2 inside? Oh, 2 and the other value. Holy crap. Oh, my bad. Yeah, if n is larger than 1, res.append, and then we return res. Yeah, it's my bad. It's my bad. Yep. Yeah, I don't know. It's oversight. But this is cheating, right? I consider this is cheating because you get all the prime down already. You get it down already. It doesn't really, right? It's like cheating. Not sure if that's the right way to do, but yeah, we got this. So, feels like cheating. Feels like cheating because we simply pulled down all the primes smaller than 316 and use that to factor each number in nums. Right, once we do that, we use union find to group all the indices, all the unique indices, all the indices that share at least one prime factors. There are a bunch of edge cases. First of all, if the size of nums is 1, the problem, right, defaults the answer to true. If 1 exists in nums and it is not possible to connect with it, we shall always remove duplicates. Right, this is the overall. We take on to factor it. No, we take O1 to factor it. Then we take on to go through it. Anyway, this is O union find. Some reverse Ackermann function. I don't even know what that means. All right, we put it here, and we have to go through this tomorrow, because that's not fair, right? That's not fair. But I think, all right, is everybody doing the same way? Factorization first. Yeah. Yeah. Consider union final. Yeah. How do you factor? Yeah, I always forget this last part. Yeah, I think we hit the right thing. It's just implementation wise, right? Implementation wise, you have to check for a lot of edge cases. They just basically starting from this. Is it? I don't know. I mean, is this a faster way to do it? Maybe it's because I did one more round of union find. That's kind of why. I don't know. But if maybe I don't need this, right? Because every single time you're always go for the same one, right? So they all go that one. And then if at the end, yeah, you have a bunch of factors, and then they all just, maybe, I don't know, you want to give it a shot? Like, you know, say, I don't do this. Is this gonna right, and this is gonna be right? No. At least my way of doing it, you have to. You have to. Yeah, you have to. Ah, okay. That's the way. There's a better way. Wait. How'd you union then? Oh, a union here. All right. I think everybody's doing the same method, so I should find. Oh, that's pretty good. I solved it. Didn't really expect to solve this. but yeah, this is absolutely necessary in my method. But did they do it? That was the question you were asking, right? I don't think they did another round of union though. A find though. It didn't merge. Well, I did a union. Oh, look at that. Look at that. I think this is to get the number of elements. Huh. Interesting. So I don't have to go through this. Hold on, let me think. Union. So instead of doing the rank, we'll count number of elements in each group. Let's start with 1. So instead of rank, we'll count. If this, if this, so if count this is larger than count this, we set a parent, right? And then if otherwise we set if count this is larger or equal to, then we self.count px plus equal to self.count py. Then we can do else. Then this is not necessary. So then we'll do all this, then we can ignore this, then we just say return dsu dot count dsu dot find 0 equal to len unique nums. The hell? Interesting. Not sure, but so far these look... No, they're not right. I followed it though. dsu.count. I'll union the two. So if count is equal, I'll set the parent. Right, so the parent, and then I'll set the count. I don't know, what did I do wrong? Fy. Right, if parents equal, now we don't do. If it's not equal, if this is smaller than this, we'll swap them. So y will be x, right? And then count or plus equal to count this. Oh, I think this has to do it here as well. So py should add it to px. There we go. There we go. Use count. Update. Use count of the size of each group instead of ranking to implement union find. This way we can immediately obtain the size of the final connected graph. Courtesy of okay. So now let's try this one. Oh, I know this one. Let's try this. Oh, I still have it open. Okay, give it a shot. Count. Faster. Much faster. Oh, Python is slow. So slow. Alright, that will be it. Yeah, these days always an hour and a half. I don't know. It just takes so long. Alright, I will see you guys tomorrow. Adios.